Hello, my name is Donald Chicino, and this is my teaching demo for scalars and vectors. Thank you very much for viewing. Today I'd like to talk to you about two new mathematical objects. A mathematical object is simply the type of thing that we will do mathematical operations on. The first mathematical object that you learned about was a number. And for numbers, we can add them, subtract them, multiply them, and divide them. So, the two mathematical objects that we're going to be talking about today are scalars and vectors. The first one is called a scalar. Okay. Now, a scalar has two parts to it. First part is the magnitude part, simply a number. For instance, 10.7, maybe 5.2, pi, and 3 are all possible numbers for a scalar. The second part of a scalar is the unit. For instance, it might be 10.7 kilometers per hour, might be 5.2 degrees Celsius, it might be pi radians, and you may have 3 bananas. All of these have a magnitude component, how large, how much, and they also have their unit, kilometers per hour, degrees Celsius, radians, and bananas. So, all of these units are a scale. How much of something that you have, hence the name scalar. And really, that's all there is to scalars for our purposes at this point. So, basically, it's a magnitude, how much, how large of something, and your unit attached to it. Now, a vector is a little bit more complex. It also has two parts, and the first part to a vector is a scalar part. We have a size and a unit. Let's take an example of 10.7, again, kilometers per hour. How fast you're going, your speed. Now, for this to be a vector, we also need the direction component. And let's say that we're traveling north. And this represents our vector. We have 10.7 kilometers per hour. Direction is north for the vector. The way that we represent a vector is with an arrow. We have the beginning, the end point is the arrow point. The arrow points in the direction of the vector itself, and the length of the vector is going to represent the magnitude of the vector. For instance, this vector might be 1 centimeter is equal to 1 kilometer per hour. If we want to represent this vector, this one seems to be pointing true north, and if it's 10.7 centimeters, that would represent our vector using this scale. Now, we have an idea of what a vector is. A question that immediately pops to mind is, okay, well, why do we need vectors in the first place? Let's take an example. Let's say there's a river. It's flowing from west to east. And I would like to travel across this river. I have a little boat, and I would like to start on the south shore here. And I would like to end up on the north shore. Now, the river is flowing in this direction, by say 15 kilometers per hour. And let's say that my boat, which will be traveling in this direction, northwards, is capable of 10 kilometers per hour. Now, if we think of this problem, as soon as I start off in the boat's going to start moving with the water as well. And instead of ending up here, I'm going to end up down shore somewhere. With simple numbers, we can't really solve this problem. I may also alternatively want to know what angle I need to point my boat at so that I can actually land directly north of the point at which I began. Now again, numbers aren't going to be terribly helpful in and of themselves. Vectors are one way that we can actually solve this problem, and many other of the problems that we're going to experience and come across and learn about in physics as we proceed with this course. One way I like to represent this with students now would be to have two students. One represent the flow of the river, the other represent the course of the boat, and have them walk across the classroom in pairs and get the physical push of one another and see how they're not going to go in the direction that they'd like to. And conversation at this point is usually pretty good. Surprisingly, some of the students will come pretty close, or even exactly close to what is needed for a vector, really how a vector is going to be useful and how we can start to mathematically operate with them. All right, starts getting them thinking about vectors. All right, so as I stated before, the first mathematical object that we learned about was a number, and the operations that we have for a number are straightforward. We know addition, subtraction, multiplication, and we have division. Scalars have the same four operators: addition, subtraction, multiplication, and division. The difference between a scalar and a number is that my units had better be the same. For instance, I can't add 10 kilometers per hour to my 3 bananas. That would be problematic, to say the least. Vectors also have four operators. However, they differ from the other two. We have addition, we have subtraction, we have two types of multiplication. The first one is called cross product, and it is represented by a normal x. The second is called the dot product, which is represented by a dot, which we sometimes see for regular multiplication with numbers. For the vector, there is no division operator. This operation does not exist for vectors, only these four. Alright? So, what I would like to talk about is the first operation for vectors, addition. So, why don't we start with that? There are two ways that we like to do this. One is called the graphical representation of vector addition. So, let's take some vectors, throw them up on the board here. So, there are three vectors on our board represented. Now, what I would like to do is talk about how we actually add these graphically. First thing I'd like to do is put our Cartesian coordinate system in here. That's our x and y axes. X, y, y, and our origin. Now, these vectors are living in this plane. What I'm allowed to do is move these vectors around as long as I keep them in the same direction. What I would like to do is move this vector to the origin. And that's what I'm going to do. Just slide it along, keep the same direction, so it'll be parallel, and the same length. And move it over there, so I'm going to erase it. Now, the way that we add vectors is head to tail. This is the tail, this is the head. So I bring the next vector over here, put its tail here, its head goes there. Similarly, we'll take the third vector and move that one over here. Now, we've added our three vectors. What these three vectors add up to is a new vector. It's going to start at the origin, at the tail of the first vector, and it's going to go to the head of the last vector. And this is our new vector. This is what these three vectors add up to. Similarly, the same way you can add numbers in any order, you may add vectors in any order. It does not matter what order you add them into, you will always come up with the same resultant vector. Now, perhaps you can see that there's some difficulty with this process. One, we are going to have to measure each individual vector, move it, keep the angles the same, etc. As you add more and more vectors, it's going to move more from a physics problem into an art project. Similarly, the other problem is that you can see that there's a lot of opportunity for errors here, getting angles slightly wrong, the measurements, etc. So there's a way to actually circumvent, go around these problems, and we have a process that is much more accurate and in the long run quite easy. So let's talk about that. And that process is called vector decomposition. What we're going to do is take a vector and break it into two parts, one along the horizontal axis and one along the vertical axis. Okay. So again, let's draw an axis and we'll place it in our Cartesian system. For now, for simplification processes, points, we're just going to stay in the first quadrant. And so we have our x and y and origin here. Now these could be actually anything. It could be west and east, north and south, for instance. It could be P and Q. Whatever works for your system, whatever problem that we're working on, we will use the labeling system that's convenient. X and Y are nothing more than labels. It could be I and J, east, west, north, south. But for now, let's just use X and Y. And let's place a vector in here. We'll start at the origin, and we'll bring it out into our XY plane here. Now what I'm going to do is I'm going to name this vector. Our naming convention is that we normally name a vector with a single letter, or sometimes two letters. One would be at the beginning point, and the second would be at the end point. So let's say that this is point P. And the origin we like to call point O, because physicists are incredibly creative all the time, and it's a very good name, O for origin. So this vector could be named either OP or R. Now you notice, over both of the vector names, I've placed a small arrow. This lets us know that this is a vector, not a variable, for instance. In your book, in other books, sometimes you'll see it written in this manner. Other times it'll be written in bold. So you'll see R bold or OP. Bold. Now as you can see, this gets a bit redundant and difficult to write. The arrow is nice and apparent, so for board purposes, we like to use the arrow to keep it separate from just the number or variable, for instance. All right. The other thing that we need here is we have the angle theta. This is measured counterclockwise from the horizontal axis, and this is convention. So every physics problem that you see in any physics book from now on, this is the way that they'll do it. So this is the way that we shall actually do it as well. All right. So you can represent the vector with the R theta or the OP. Okay. Now, we're going to move on to the actual decomposing of an example vector. So again, let's put it in our XY plane. Okay. And we're going to call this vector R. And let's say that it is at 30 degrees as measured counterclockwise from our horizontal x-axis. And the magnitude of this one is going to be 10 kilometers per hour. Now the way that we differentiate just the magnitude of the vector from the vector itself is we will call the vector magnitude. We represent it either by one of these two schematics, either the R, non-bold, arrow missing here, and in your book non-bold, or the vector name itself, the arrow above it, with our absolute value signs around it. Okay. Now, this vector magnitude is therefore 10 kilometers per hour, and our theta has the value of 30 degrees. The next step in this process is for us to drop two perpendiculars down. One is going to go from the head of the arrow. We're going to drop that perpendicular down to the x-axis. The second one is going to come perpendicular to the y-axis. And what we're going to do is we're going to place two vectors along these lines. Okay. Now you can see, with the rule of being able to slide vectors around, we'll slide this vector over here. And you now see that if we add this vector, which is purely along the x direction, and add this vector, which is purely along the y direction, we get the r vector. This is called components of the r vector. This would be the x component. We'll denote it r sub x. And this one would be the y component, and we'll call that one r sub y. Okay, they are vectors. The direction is along the axes, respectively x and y. Now, you'll notice something here. We are back to our old friend, the right triangle. Whenever that happens, the Pythagorean theorem is going to come to play for us. So let's take a look, review, and we're going to do some relabeling for ourselves. So, if you remember from your geometry and trigonometry days, when we have a right triangle, we have side C, angle C, which is your right triangle side, your 90-degree angle. We're going to have angle A and side A, and we're going to have side B and angle B. Now, what I'd like to use is change the labeling of this slightly, actually, so that it is more trig-friendly for us. We're going to call this our hypotenuse, which I'm sure you've all heard before. This is our angle theta. And we're going to use this as the angle about which we're speaking. So the side that is opposite of the angle is over here. We'll call that opposite. And similarly, this side is adjacent to that angle, so we will label it adjacent. Now, if you remember your Pythagorean theorem, we have c squared is equal to a squared plus d squared. Now, if we use our labels over here, we're going to have that the hypotenuse squared is going to be equal to the opposite side squared plus the adjacent side squared. So we've done a little bit of relabeling, and we have our Pythagorean theorem set up in the label system that we have incorporated over here. Similarly, we have our trig identities, sine, cosine, and tangent. And let's look at them in the system. So for sine of theta, that's going to be equal to the opposite side over the hypotenuse. The cosine of theta is going to be equal to the adjacent side over the hypotenuse. And finally, our tangent of theta is going to be equal to the opposite side over the adjacent side. And this is what we're going to be using to decompose our vector. Sine identity, our cosine identity, the tangent identity, and our Pythagorean theorem hypotenuse squared is equal to opposite side squared plus adjacent side squared. Now going back to our example vector that we had here. We have that R vector at an angle 30 degrees. The theta is equal to 30 degrees. And the magnitude of R, we stated, is at 10 kilometers per hour. We had dropped our perpendicular and brought our perpendicular across over here. So we have our r sub x vector and our r sub y vector. What we're going to do is solve for those two magnitudes. And we're going to use the identities sine and cosine to do that. So we have that the sine of theta is equal to the hypotenuse, equal to the opposite over the hypotenuse. Now, let's bring this vector over here again. So we have Ry over here. And we see that Ry, R sub y, is our opposite side. So we're going to have that sine of theta is going to be equal to the magnitude of R sub y, which is R sub y without our arrow, over the hypotenuse magnitude, which is R without the arrow over it. R. Now let's solve for R sub y. R comes up, and we have that R times the sine of theta is going to be equal to Ry. So the magnitude of R times the sine of the angle theta is equal to the magnitude of R sub y. Putting in our numbers, we're going to have that 10 kilometers per hour times the sine of 30 is equal to 5 kilometers per hour. 5 kilometers per hour. Okay. And that's our first value. Now let's solve for the adjacent side, the R sub x value. It's going to be cosine of theta this time. And it's going to be the adjacent side over the hypotenuse. This time is going to be the cosine of theta is going to be equal to R sub x over R. We have the magnitude of R sub x over the magnitude of R. Bring the R up. R cosine of theta is going to be equal to R sub x. So the magnitude of R times the cosine of the angle theta is equal to the magnitude of R sub x. Putting our numbers in again, 10 kilometers per hour, cosine of 30 degrees, and it's going to give us 8.66 kilometers per hour. So, we can now represent this vector with these two values. Previously, we could represent the vector as two values, the first being 10 kilometers per hour, and the second one being the angle theta, 30 degrees. Now what we can do is place in the two values for R sub x and R sub y. We have that R sub x is equal to 8.66, and our value for y, R sub y, is 5. And those both have the unit of kilometers per hour. Okay? So we have what appears to be our normal way of representing a point in the plane, Rx plane. The x value and the y value. So, I have already decomposed three vectors, and let's take a look at their representations in this system. So we have that first vector was the values 10, and it is 2.1. The second vector is 7.2 and 5.6. And the third vector has the decomposed values of 2.5 and 3. These are all kilometers per hour. So again, we have three vectors that have decomposed. We'd like to add these three vectors together. And this is where it's actually going to become quite simple. Let's look at the x values first. Now, we add vectors head to tail. Let's just look at along the x-axis. Starting at 0. The first vector has a length of 10. What is in there? 10, and again, they're all kilometers per hour. Second vector has a value of 7.2. We just add that here. Right along the same axis, 7.2. And finally, we have 2.5. 2.5. And as you see, what winds up happening is, since they all lie along the same axis, it's essentially numbers on a number line, all we need to do is add the values of these numbers. We have 10 plus 7.2 plus 2.5, giving us 19.7 kilometers per hour. Similarly, along the y-axis, the horizontal axis, vertical, we are going to have the same situation. We have 2.1, again, all kilometers per hour. We're going to have a second vector of 5.6, and third vector of 3. Adding these three values together, 2.1, 5.6, 3, is going to give us a value of 10.7 kilometers per hour. So what we've done is taken three vectors, decompose them into their pairs of numbers, and you add the numbers and you get your resultant vector. Has the values of 19.7 and 10.7 in kilometers per hour. Now, what we can do that we have these two values is we can go back to the other way of representing a vector, where we have the magnitude and the angle theta. So let's go ahead and do that. We'll call the resultant vector of these three vectors added together big R. Okay. So the magnitude of big R is just going to be R. And we know that R squared is going to be equal to R sub x squared plus R sub y squared. Take the square root of both sides, that square root goes away, and we have the square root of R sub x squared plus R sub y squared gives us the magnitude of R. So we have 19.7 kilometers per hour squared plus 10.7 kilometers per hour squared, all square root. When we work this out, our value comes out to be 22.4 kilometers per hour. That is the magnitude of our resultant vector. Now what we can do is solve for our angle theta, and we're going to use, since we have the opposite and adjacent sides, let's use the tangent. We have tangent of theta is equal to the opposite over adjacent. The opposite side is going to be the y value, horizontal value, 10.7 kilometers per hour. The adjacent side is 19.7 kilometers per hour. The units are going to cancel out. We have our pure number, 10.7 over 19.7. What we do is take the arctan for both sides. So we're going to have theta is equal to the arctan of 10.7 over 19.7. And when we crank that through and solve, we have that theta is going to be equal to 28.5 degrees. And you can see that this process is going to be a lot simpler than trying to add vectors graphically. We can add 10, 15, 100, 1,000 vectors relatively quickly, and we can keep as much of the accuracy as we need, as opposed to the other one where lots and lots of inaccuracy will start to creep in. So that's the beginning of vector addition and an introduction to scalars and vectors. Thank you very much for viewing. I look forward to hearing from you.